Today I'm going to present you our paper called DSEG-LIME, which is about user-driven granularity to enhance the image explanation with our hierarchical composition. My name is Patrick Knab. I'm a PhD student at the University of Mannheim, and this work is joint work with my colleague Sata Markon and my supervisor Christian Bartelt. So before I'm starting with the actual topic, I quickly want to recap why explaining an AI is important. So AI models rely on input features to form their predictions across different modalities, such as images, where we can use individual pixels, or we can also aggregate pixels to superpixels. For text, we have words, phrases, and for tabular data, we can use the individual attributes, or we can combine those attributes or use those columns themselves. However, there's now the critical question, which features are most influential for a specific prediction? So for example, if we are in the medical image domain, what aspects of a CT scan can need an AI model to classify it as indicative of pneumonia, which is an illness in the lung? And as I said before, for features, for images, we have feature attribution techniques that aim to identify those most relevant regions within the image. And down below here, we see one example. So this is a CT scan of a lung, and a human annotator here in red annotate this image that this is the specific area for pneumonia. And 7C maps, mostly known by GradCam, they highlight the areas where the model focuses its attention. So it looks into the model itself. So that's the reason why it's also called model specific. On the other hand, we have superpixel explanation. And those superpixel-based explanations, the most known is LIME, segments the image into superpixels, and then it calculates the importance for each superpixels for the explanation. What we can already see is that for both two explanations, so for 7C maps and for superpixel-based explanations, the explanation somehow aligns with the ground truth data. So if the human annotator tells us this is the most relevant area for classifying it as pneumonia, GradCam as well as LIME have correctly identified those two areas. So why should I trust you? This is the known title of the famous paper LIME, which is the abbreviation for local interpretable model-agnostic explanations. So it makes local predictions, so around the local instance X, and model-agnostic, meaning it can explain a bunch of models without relying on the model-specific properties. Since this work mainly builds on top of the LIME framework, I quickly guide you through these four main steps of LIME to know at a later point of time where our DSEG-LIME framework sets in. So in the beginning, we have the feature generation process. And for the rest of this presentation, I will stick to images specifically. We have our image X, and we can either calculate the importance for each individual pixels, but that this raises exponentially. So we are going to segment the image into similar segments. And those segments, so this image segmentation generates our superpixels, and we use those superpixels for the explanation process. And there's also binary array, and this is the number of superpixels that we end up in the end, indicating whether one superpixel is turned on or off, but that's mainly important for the sample generation. In the sample generation, we're perturbating the samples to set I. This perturbation can happen by taking the mean value or taking a specific value like black or white to exactly. And as soon as we have perturbated those samples, we put them back into the model F that we want to explain. And therefore, this process captures the local behavior of the model F around the neighborhood of the original instance X. Feature attribution is the main part of this framework. Here, we fit or we approximate a model interpretable model G that minimizes the following loss function. And here it's mainly important to look at the kernel. The kernel is a function that measures the proximity of the perturbated sample set I to the original instance X and gives higher rates to samples that are closer to X and also the other way around. And later, we use the coefficients of G to represent the contribution of each feature. So that's in the end our actual explanation. So the top K features with having, for example, the highest absolute weight form our explanation. So if we go back, those three coefficients representing the superpixels were the most influential ones. But I do not trust you. So what's the role of segmentation in LIME in general? So on the right side, you see the popular example of a dog playing guitar, which is widely used in the XAI domain, especially when it comes to LIME, because they have shown their approach based on this image. And here we have three classifications that are three classes from the ImageNet dataset. So acoustic guitar, golden retriever, and electric guitar, with 4 different segmentation techniques. So quick shift, which is in the basic vanilla LIME implementation, slick, Felsenswarp, and watershed. All those 4 segmentation techniques are widely used in the literature and therefore our main comparison. As we can see, the image explanations, I wouldn't say are not that faithful, because for me, those superpixels seem arbitrary. So for example, if you look at the explanation for acoustic guitar, I would not say at all that this makes sense, that this could be indicated acoustic guitar. Same for the golden retriever or for the electrical guitar. And this is consistent across several segmentation techniques, even though, for example, watershed is slightly better or slick, but they are still not that what we would expect. In addition, the LIME framework is static, meaning we users, we have no control of the granularity of the segmentation. So for example, if we are looking now at the image explanation of the class acoustic guitar or slick, I would say this explanation is still too huge, let's say. So it's still not capturing, from my understanding, the most important parts of the image. So I want to have finer more granular explanations. So that's also not possible with LIME yet. The only thing that you could do is to change the hyperparameters of slick and run LIME from scratch. In addition, we call them non-human recognizable concepts. We humans have different kind of concepts in our mind. Like, for example, if we have the concept car in our mind, we know that this super concept consists of multiple smaller concepts like windshield or wheel or chassis or whatever. However, if you're looking at those superpixels, we wouldn't say that those are actual recognizable concepts. So for this, that's our approach, DSEG. And what we can clearly see is already that the acoustic guitar actually covers, from our understanding, the most influential area for acoustic guitar. For the golden retriever, still the whole golden retriever, even though if we also see some part of the body of the human, I don't know why. And regarding the electrical guitar, I'm not playing guitar, so I can't name you how these parts are called, but definitely different to the other parts of acoustic guitar. So data-driven segmentation, that's the name of our method. And our motivation is that thanks to the recent advances like techniques of segment anything, detour, crowning dino, and there are way more segmentation techniques, they offer powerful segmentation capabilities that now span over multiple domains like imaging data, daily data like traffic control data, whatever. And the objective is to segment images into meaningful regions that align with our human perception, so semantic segmentation. And we can segment an image from coarse objects, like, as I said before, a whole car, until to fine details, like individual car parts. And now our idea is to make use of this powerful segmentation to integrate into methods like LIME, but to also make it dynamic. So our approach builds within LIME a hierarchical segmentation framework that guides LIME through the different levels of granularity. And what we can see is that we generate explanations that match more to human conceptual understanding, and it also allows users to adjust the level of granularity during the explanation phase itself. So how does it work? Let's consider again the basic LIME framework. So in the beginning, we have our image. We take this image and put it into our feature generation. So as I said before, we segment the image. After we have got the segments, we sample those segments and approximate a model that we can interpret to get our explanation. We leave LIME mainly untouched, but we are rather focusing on the feature generation and sample generation phase in the end. So what we are doing, again, our motivation is that we have a human intuition that establishes relationships between concepts of different identifiable objects, like the a relationship between the car and its windshield. So the car is the whole body and the windshield belongs to the car. And the idea is to utilize this relationship of features in LIME's image explanation process itself to allow a top-down approach of the segment granularity. And how are we going to do that? We create an internal hierarchical tree structure through composition, where each node, we represent one feature of the segment. So if we have the segments, we also have the nodes in our graph. The edges between those nodes represent the relationship between those parent and children segments. So we call a node a parent node if it's the highest segment possible, and all nodes below are called children segments. And how this is going to be constructed is shown in the next slide. And the depth defines the granularity of the explanation. So in the beginning, we start with only the parent segments. And if we have a depth of 2 or depth of 3, we consider in each next iteration also its children nodes. So yeah, it's not static anymore, it's dynamic. So after each iteration, only children nodes with the top K feature scores are added. So it's not, as I said before, not static anymore, but we can repeat this process n times. So we can repeat it to the depth of the hierarchical tree in the end to reach the bottom line of the finest possible segments in the end. So that's the process. So let's suppose we take this image as input and we give it to EfficientNet V4, which originates from the ImageNet dataset, so having 1,000 classes. If EfficientNet V4 classifies this image as hypercar. And now we are interested in why is it classified as a hypercar? Because there are other classes for cars like pickup truck, normal car, I don't know, so there are multiple classes of cars. And in the beginning, we put the plain automatic mask generation, for example, provided by a segment anything, on top of the image, and we end up in such an image, for example. Based on this image, we can construct our hierarchical tree within the DSEG-LIME framework, and the dark nodes represent the highest possible parent segments, and the light gray nodes are their corresponding children. So in the first iteration, we only look at those dark colored nodes. So as I said before, they correspond to one segment. And in the end, in the first iteration, we are only looking at these segments that we can see here. If we would stop here, we would get as the explanation only the whole car. So we would end up having exactly this whole car. However, I wouldn't be happy with that because we still have a lot of different classes of cars within ImageNet. So I would like to have more specific concepts. So in the next iteration, we now know that the car is the main important superpixel in the first iteration. So we add its children nodes in the next iteration, recalculate or refit the interpretable model G, and then get the explanation. So in the end, we end up with this explanation. So we see now again the car, but without its windshield, lights, wheels, etc. So yeah, that's how this hierarchical framework works within LIME itself. To test this idea, we have made an extensive quantitative evaluation and applied the DSEG framework to LIME, S-LIME, G-LIME, and Bay-LIME. S-LIME, G-LIME, Bay-LIME are further advancements of LIME itself because they try to improve the issue of having instability issues. Because nowadays we know that LIME has several issues like instability, fidelity, locality, and S-LIME, G-LIME, Bay-LIME improve the stability issue. And what we wanted to investigate is whether S-LIME, G-LIME, Bay-LIME are further supported by having better segments. For the baseline, we compare against traditional segmentation techniques like SLIC, Felsen-Sort, Watershed, and Quickshift. So those are the 4 segmentation techniques that I've shown you in the beginning with the dog playing the guitar. And for segmentation approaches, we tested segment anything 1, segment anything 2, and the detour segmentation method. And for the dataset, we mainly conducted our experiments on the imager dataset. So our quantitative and qualitative experimentation is mainly done on the imager dataset. However, we also have tested it on zero-shot classification with CLIP on other datasets as well, and it still works and performs quite good. And the used pre-prompt models are EfficientNet, Vision Transformer, and ResNet to have different model architectures that we can test. For the evaluation and metrics that we used, we oriented on Nauta et al. And they proposed or they summarized quantitative XAI evaluation metrics that are used or that can be used for XAI evaluation. And we have here 5 main classes. Correctness. For correctness, we introduce for the first 2 parts noise to the model itself by, for example, shuffling the weights of the model or shuffling the prediction of the model. For single deletion, we replace the explanation with a specific background image, for example, simply water or the sea. For incremental deletion, we measure the area under the curve when incrementally deleting the most important pixels and replacing them with dummy values. For output completeness, we only give back the model, the explanation itself, and everything but the explanation for deletion check. For compactness, we measure the fraction of the image used as the explanation. For consistency, we introduced slight noise based on the image itself. And for representation stability, we run the same explanation multiple times and observe its variation. And for contrastivity check, we use another model. So for example, if we are doing our evaluation on EfficientNet B4, we use EfficientNet B3 and give the explanation of B4 into B3 and see whether it still predicts the correct class or not. And we do that for preservation check and deletion check. And the last metric that we are going to that we used was computation time. So we evaluate DSEG-LIME that they are both minimal and complete. So we look at different perspectives on this problem. Regarding the results. So now we are mainly sticking to EfficientNet B4. And for that, we have selected 50 random images from the ImageNet dataset, where each image represents a unique class. And we compare it, as I said before, against S-LIME, Bay-LIME, G-LIME, and LIME. And those are the abbreviations, so LSGB, against other segmentation-based approaches. And here we are mainly looking at the explanations generated within DSEG-LIME with segment anything 1 and segment anything 2. So let's start with the results for segment anything 1. So again, this means we use SLIC within LIME, we use SLIC within S-LIME, and so on and so forth. And we have here split the table again into correctness, output completeness, consistency, contrastivity, and into 2 different kinds of tables. So the table below measures numeric values like the area under the curve, which is a numeric value where we use the mean value simply, compactness the same, representation stability and time as well. And for the table above, we measure the correct class. So here we can have up to 50 points, so each point for one image, and the higher the better, whereas here the lower the better. And what we can see is that DSEG-LIME consistently, or not consistently, but mostly outperforms the other segmentation approaches within different LIME techniques. And here down below as well, even though what we definitely have to say is that the computation time is slightly higher than other segmentation methods except of quick shift, but that is due to having the problem of running segment anything beforehand, which takes some time. Yeah, there's, for example, phase and shot of watershed simply quicker. And regarding compactness, we tested this approach for a level granularity of 1. So if we consider the car example again, we are only looking here now at the whole car and not one step deeper. So we also run experiments with different depths of the hierarchical tree. So those are in the appendix of our paper. And then we can greatly decrease the compactness again and are even better than the other approaches. And also for segment anything too, the results stay the same. Yeah, still offering the best solution. For ResNet 100 and for Vision Transformer 384, the results are similar, although the results are less pronounced compared to those observed by EfficientNet before. But this issue is mainly due to the fact that we segment the image before it gets fed into the model. So for example, ResNet 100 and Vision Transformer 384 has a smaller resolution than EfficientNet. So if we use bigger models, we have our models that accept the higher resolution, we can also profit more from the segmentation performance of, for example, segment anything. But still outperforming mostly the others. For qualitative results, we did a user study where we followed the approach of Kromik and Schassler. And the study overview was that we conducted experiments with 87 participants that we recruited over Amazon Mechanical Turk. And those were asked to evaluate the explanations for 20 randomly selected images from our dataset of 50 images. And we gave them for each image 5 different explanations. So we have the DSEG-LIME explanation, then the SLIC, quickshift, watershed, and phase swap, all within the basic LIME framework, and asked them, given these explanations and given the original image and given the prediction of the model, which explanation best fits to their understanding. And they were, and they did this by by rating them from a scale of 1 least effective to 5 most effective. And yeah, the ratings are based exactly on the clarity of the explanation and its alignment with the predicted class. Regarding the results, here we can see the interquartile range plot for DSEG-LIME and the other segmentation techniques as well. And the average rating here in red. So regarding the average rating, DSEG-LIME got the highest average rating and quickshift right here the lowest with only 2 with 2. And with having the 0.75 percentile and 0.25 percentile, we are still better than the others. When talking about absolute terms, here this plot represents the count of having most effective, so 5. And what we can clearly see is that DSEG-LIME most of the time was rated the best. Before I'm summarizing this presentation, I want to also show you a quick case study again, where one can use DSEG-LIME to explain the wrong class. Even though if the explanation is not exactly wrong, it's not a misclassification. But in this case, we can see that's an animal which has zebra-like patterns, but the actual animal is still a horse. But however, EfficientNet before classified it as a zebra. And now we are interested in which concepts or which superpixels led to the misclassification. And again, for the def of 1, we get the whole animal. So it's the same thing like that we get for the hyper car or sports car. But we are not happy with this explanation because we want to have more or finer details. So in the second hierarchy, we get now its head and its tail. And those are exactly the parts that represent the zebra-like patterns. So that's just one case study that we did, but we saw that if you utilize DSEG-LIME and its hierarchical approach, that we can find more fine-grained features that contribute to the explanation quality in general. So what are the implications for XAI? So beginning with foundation models in general. So foundation models can enhance explainability. So as has shown by our host, Nick Kröger, for example, LLMs can also be used as foundation models that can boost the explainability within frameworks, especially in concept-based models for concept creation, as we have shown here with DSEG-LIME. In addition, if we use such foundation models, we call it advanced models aid interpretation. So complex models now can help explain similar models, like a teacher-student approach. Our student is now the simpler model, like EfficientNet before, and our more complex model is now our foundation model. However, it arises a new challenge. So we've got now another black box. So we moved from the simpler black box to a more complicated black box. In this case, our new black box is the large foundation model. In addition, we think that the role of LIME is further evolving. Since now LIME mainly serves as a general framework, there exist so many works building on top of LIME. They extended to voice data, they extended to multimodal data, they extended to so many use cases. So it has now a broader application, and that's the evolving realm of LIME, and it's not anymore the simple LIME framework that was proposed in 2017. Regarding the conclusion and future work, so our achievements were that we demonstrated that our framework demonstrates top state-of-the-art performance regarding qualitative evaluations, and it also produced, when looking at the qualitative user study, more meaningful explanations compared to other existing methods. It still remains versatile, meaning it can be applied across all vision models, which is quite important because there exist a lot of works also utilizing foundation models, but they strictly rely on the internal workings of the model itself. But here we are completely model agnostic, meaning we do not have to access the model internal structures itself. And we offer the user an interactive control to adjust its granularity, which is quite new because now we move from a static limitation to being a dynamic framework. For future research directions, so one can look at multimodal expansion. So one can integrate multimodal foundation models similar to DIME to enhance its interpretability and across different data types. So not sticking mainly on one modality anymore. And another interesting area is to use foundation models, especially generative models, to refine the data sampling. Because if we look back to the initial LIME top-down approach, when we sample the data, we take, for example, for images, simply the mean value, or we have a replacement value. However, this is not good for proximity because if we are looking at the sampled images and the original image, we see great differences. So that's the reason why we have some issues with locality and fidelity. So one idea would be to use generative models to improve this sampling process by utilizing their strengths. Those are my sources. If you want to stay connected, here's my LinkedIn QR code, preprint on archive. Thanks for your attention, and yeah.